All right, welcome back to the deep dive. Today we're taking a look at something that caught my eye. It's a really interesting new approach to video embedding.
Oh, cool.
Specifically for generative models. How do we represent videos in a way that AI can use to create new content?
Right.
And the paper is called Regen, Learning Compact Video Embedding with Regenerative Decoder. Quite a mouthful. But the core idea that jumped out at me was this move away from trying to recreate videos perfectly, pixel by pixel, when you compress them and decompress them, and instead focusing on making videos that are believable.
Yeah, that's a really interesting shift in thinking because, for years, the whole focus has been on fidelity, right? Like, how close can we get to the original video after we've compressed it and then unpacked it again?
Yeah, exactly.
But this paper kind of throws that out the window and says, well, what if we just need the essence of the video, enough to generate something new, something plausible? Like, does it really matter if every pixel is exactly the same if the AI can create something that looks and feels real?
And what's really striking is the potential improvement in efficiency they're talking about.
Oh, yeah.
Up to 32 times greater temporal compression compared to what's currently out there, which is usually stuck around 4x.
Wow.
That's huge. That's like fitting 5 times more video information into the same space.
That's a game changer, especially when you're working with these massive generative models that just eat up GPU memory.
Totally. And for anyone out there who's, trying to generate videos in real time, that kind of compression could be a huge deal.
Absolutely. Real-time video generation is really computationally intensive.
It is. So it's exciting to see research pushing the boundaries like this.
Definitely.
Okay, so let's unpack how they actually achieve this. Before we dive into Regen specifically, can you give us a quick overview of the world of latent diffusion models, or LDMs? Like, how do they work and where does this whole video embedding thing fit in?
Sure. So LDMs have become kind of the standard for generating images and videos these days. And the basic idea, it's kind of counterintuitive, is that you take your input, let's say a video, and you gradually add noise to it.
Okay.
You just keep adding noise until it basically becomes pure static, like you're watching a TV with no signal.
Right, just random pixels.
Exactly. But the clever part is that you then train a model to reverse this process.
Ah, I see.
So it starts with the noisy mess and learns to gradually remove the noise step by step until it generates something that looks like the original video.
And this all happens in this compressed latent space, right? Like, it's not working with the full resolution video the whole time.
That's right. The whole point of the latent space is to reduce the dimensionality of the data to work with a more manageable representation.
Okay, so that's where the video embedder comes in.
Exactly. The video embedder's job is to take that raw video and squeeze it down into this lower dimensional latent representation that the diffusion model can then work with.
Got it. And the paper points out that existing video embedders, like MagVi-ITV2, which is a popular one, they're pretty good at compressing spatially, and like reducing the size of each frame.
Yeah, you can typically achieve around 8x spatial compression without much loss in quality.
Right. But when it comes to compressing across time, like reducing the redundancy between frames, things haven't really progressed as much, have they? It's usually stuck around 4x.
Yeah, that's the bottleneck. And it comes down to this fundamental trade-off in compression, right?
Okay.
The more you compress something, the more information you potentially lose. And with traditional encoder-decoder setups, that loss of information translates to a worse reconstruction when you try to decompress it.
So if you compress too aggressively in the temporal dimension, you end up with, like, jerky motion or weird artifacts, things like that.
Yeah, exactly. It's like trying to tell a story by only describing every fourth sentence.
Yeah.
You might get the gist, but you lose a lot of the detail and nuance.
Right. And this is where Regen comes in with a totally different approach.
Yeah, this is where it gets really interesting.
Instead of trying to cram every detail into the latent space, Regen basically says, hey, for generative purposes, we don't need a perfect reconstruction. We just need enough information to plausibly recreate something similar.
It's like instead of trying to preserve every single word of the story, they're just capturing the key plot points, the characters, the setting.
Exactly. And they're relying on the power of a generative model to fill in the gaps, to add back the details and make it feel real.
Right. So instead of that traditional encoder-decoder setup where the decoder is basically just trying to undo what the encoder did, Regen uses an encoder-generator framework.
Okay.
The encoder focuses on extracting the essential semantic and structural information from the video, like what's happening, where things are, and how they're moving.
And then it gets fed into the generator, which is this diffusion transformer, or DIT.
Exactly. And the DIT is where the magic happens. It takes that abstract, compressed representation and uses its generative capabilities to synthesize the finer details, the textures, the movements, the subtle visual cues that make the video look real.
So the encoder is like a screenwriter, coming up with the basic story, and the DIT is like the director, bringing that story to life with all the visuals and effects.
I like that analogy.
Okay, so let's break down the Regen architecture a bit more. What's going on with the encoder?
So their encoder design borrows some ideas from Agye TV2, specifically the continuous version. It uses these things called causal 3D convolutional blocks.
Causal, huh?
Yeah, the causal part is important because it means that the model only looks at past and present frames to predict the future. It can't peek ahead in time, which would be unrealistic, right?
Makes sense.
And to handle long videos without running into memory problems, they process the video in smaller chunks.
Okay, so each chunk gets encoded separately. And what does the encoder actually output for each of these chunks?
It produces two compressed latent frames. The first one they call the content latent, or ZC.
Content latent.
And this one basically captures the key visual information from the very first frame of that chunk. Think of it like a snapshot of what's in the scene at that moment.
Got it.
And then the second one is the motion latent, the ZZM.
Okay.
And this one encodes in a very compressed way how things are moving and changing in the subsequent frames of that chunk.
So one for content, one for motion.
Exactly. And what's really remarkable is that both of these latent frames only use 8 channels.
8 channels. It's incredibly compact.
Yeah, it really highlights how much they're able to squeeze down the information.
Okay, now let's talk about this DIT decoder. Why did they choose a transformer architecture here? You know, like we often see convolutional decoders in these types of systems.
Well, diffusion transformers have been showing really impressive results lately, especially in modeling complex data distributions.
Okay.
They're often able to outperform the more traditional UNet architectures, which are also common in diffusion models.
So they're kind of like the new hotness in the diffusion world.
In a way, yeah. And by using a DIT and framing the decoding process as a conditional diffusion process, they're basically training the model to start from a noisy representation and then iteratively refine it, guided by those compressed ZC and ZIM representations we talked about, until it generates a high-quality video.
So it's denoising, but it's denoising in a way that's informed by that compressed content and motion information.
Exactly. It's not just randomly trying to remove noise. It's guided by the essence of the original video.
I noticed in the paper that they don't always just train the decoder to reconstruct the exact input video. Sometimes they use like temporally upsampled versions or even time-shifted versions.
Yeah, that's a really clever trick. By training the decoder not only to reconstruct the original, but also to generate these manipulated versions, they're essentially forcing it to learn a more robust understanding of video dynamics.
So it's learning how things move and change over time, not just what things look like at a single moment.
Exactly, and that makes the resulting video embeddings much more powerful for downstream generative tasks, like if you want to generate new video content that's not just a copy of the input.
Okay, that makes sense. Now, feeding those compressed latent maps into a transformer decoder, especially one that's trying to handle different video resolutions and aspect ratios, that seems tricky. How do they solve that?
Yeah, that's one of the challenges they specifically address. Standard DDTs rely on these fixed positional embeddings, which tell the model where things are in the input sequence.
Right.
But if you train the model on videos with a certain resolution and then try to feed it videos with a different resolution, those fixed positional embeddings don't really work anymore.
It's like giving someone directions based on a map that's the wrong scale.
Exactly. So to solve this, they introduce a latent conditioning module. It's a bit of a mouthful, but it's basically designed to transform those content and motion latents, the Z key and Z key, into what they call a content-aware positional embedding, or XI.
Content aware.
Yeah, that's the key here. Instead of just giving the decoder fixed coordinates, they're giving it positional information that's informed by the actual content and motion of the video.
Okay, so how does this module work?
It uses a siren network. Think of a siren network like a flexible function that can map any input to a corresponding output.
Okay.
So in this case, they use the siren network to map the time coordinate of a specific location in the video frame to a feature vector.
Time coordinate. So like where in the video sequence that location occurs.
Exactly. But here's the crucial part. This mapping process is modulated by the motion latent, the ZIMA.
So the motion information is influencing how the siren network maps time to features.
Exactly. It's like saying, okay, given the way things are moving in this video, here's how we should represent the time coordinate at this specific location. And then this resulting feature vector, which now encodes time information that's sensitive to the motion, is combined with the content latent, the ZNZ, at the corresponding spatial coordinates.
So it's like creating a positional embedding that's tailored to the specific content and motion of the video.
Exactly. And this allows the decoder to understand the spatiotemporal structure of the video in a way that's not tied to the specific resolution of the training data.
That's really clever. Okay, let's talk about the results. How did Regen actually perform in their experiments?
Well, they tested it on a couple of standard video data sets, and they used a range of metrics to evaluate the quality of the reconstructions, things like PSNR, SM, and RFVD.
Okay, and those are all ways of measuring how close the reconstructed video is to the original, right?
Yeah, they captured different aspects of the visual fidelity, and what they found was really impressive. At those very high temporal compression ratios we talked about earlier, like 8 by 8 by 16 and even 8 by 8 by 32, Regen consistently outperformed MagVit V2, which was their baseline.
And MagVit V2, that's a state-of-the-art video embedder, right?
Yes, it's a very strong baseline. And what's really interesting is that the performance gap between Regen and MagVit V2 actually widened as the temporal compression became more extreme.
So the more you compress, the better Regen performs relative to the traditional approach.
Exactly. And that really highlights the power of that generative decoder. It's able to handle much more aggressive compression without losing as much quality.
And it wasn't just about the numbers, right? They had some visual comparisons too.
Oh, yeah. Qualitatively, the videos reconstructed by Regen looked much better, especially in areas with a lot of motion. Like MagVT2 would often show these temporal artifacts, like blurring or ghosting in those fast-moving regions.
Right.
But Regen was able to generate much more coherent and realistic motion, even when the temporal compression was really high.
So it's like the generative decoder is able to fill in the gaps in a way that makes sense, even when it's working with a very limited amount of information.
Yeah, exactly. It's not just trying to blindly reconstruct every pixel. It's using its understanding of motion to generate something plausible.
Okay. Now, what happened when they compared Regen to other state-of-the-art video embedders, but this time at a more standard 4x temporal compression?
Well, even though Regen was designed with those higher compression ratios in mind, it still performed really well at 4x. In fact, it often achieves state-of-the-art results, even compared to embedders that weren't specifically designed for high compression.
So it's not just a niche solution for extreme cases.
Yeah.
It seems like it might be a better overall approach to video embedding.
Yeah, I think that's a fair takeaway.
Now, one of the really exciting applications of efficient video embeddings is in text-to-video generation. Did they experiment with that at all?
They did. They trained a large-scale diffusion model for text-to-video generation, and they used Regen's 32x compressed latent space as the input. And even with a relatively small-scale training setup, they were able to generate some really impressive videos from text prompts.
That's amazing. So you give it a text description, and it can create a video that matches that description.
Yeah, and the key here is that by using Regen's 32x compressed latent space, they were able to reduce the number of latent frames the model had to process by a factor of 5 compared to using a standard 4x compression. And that translates to huge savings in computational resources and training time.
That's a massive advantage, especially in a field like text-to-video generation, which is notoriously computationally expensive.
Absolutely. It could make these models much more accessible to researchers and developers who don't have access to massive compute clusters.
Speaking of computational efficiency, diffusion models are often criticized for being slow at inference time because they require so many denoising steps. Did they find any ways to improve that with Regen?
Yeah, they specifically looked at how the reconstruction quality changed as they reduced the number of sampling steps in the DIT decoder, and what they found was that Regen was able to maintain good quality even with significantly fewer steps, sometimes even down to a single step.
Wow, a single step. That's incredibly efficient.
Yeah, it's a testament to the power of that latent conditioning module. By providing such strong guidance to the decoder, they're able to achieve good results with much less computation.
That's a game changer for practical applications. If you're trying to generate videos in real time, you don't want to be waiting forever for each frame to render.
Exactly.
Okay, let's circle back to that latent conditioning module for a second. Did they do any specific experiments to show that it was really the key to handling different video resolutions?
They did. They compared Regen to a baseline model that used a more traditional fixed positional embedding scheme. And what they found was that the baseline model really struggled when it was given videos at a higher resolution than it was trained on. It showed these weird gridding artifacts, like the model was trying to fit the higher resolution video into its lower resolution understanding of space.
Right, it couldn't generalize.
Exactly. But Regen, with its content-aware positional embedding, generalized really well. It was able to handle the higher resolution without any problems.
So that really highlights the importance of making the positional information dependent on the actual content of the video.
Yeah, it's a much more robust approach.
Okay, last thing I wanted to touch on is the chunking. You know, they process the videos in chunks,
Yeah.
but that seems like it could potentially lead to some problems.
Yeah, you're right. If you're not careful, you can end up with noticeable jumps or discontinuities between chunks.
Exactly. So do they address that at all?
They did. They proposed a latent extension strategy, which basically uses the decoder's ability to extrapolate over time. So they use the predicted last frame of one chunk to help guide the generation of the first frame of the next chunk.
It's like they're overlapping the chunks a bit.
In a way, yeah. And it seems to work pretty well. They showed some visualizations where the transitions between chunks were much smoother when they used this latent extension technique.
Okay, so they're not completely eliminating the chunking problem, but they're mitigating it.
Exactly.
All right, so Regen seems like a really promising step forward. But of course, there are always limitations. What were some of the things the authors acknowledged?
Well, the biggest one is probably the computational cost of training those diffusion-based decoders.
Right, they're still computationally intensive, even though the inference can be made more efficient.
Yeah. And while the latent extension strategy helps with the chunking, it's not a perfect solution. There's still some room for improvement there.
Okay.
And lastly, they pointed out that their decoder operates in pixel space with a fairly large patch size, which they chose for efficiency reasons. But that could potentially lead to some loss of detail in the generated videos.
Right. It's always a trade-off.
It is.
Okay. Now, for the fun part, the novel notions segment, what are some interesting research directions that you think Regen opens up?
Well, one idea that comes to mind is dynamic temporal compression.
Dynamic temporal compression.
Yeah, so imagine a system that could automatically adjust the temporal compression ratio based on the complexity of the video content.
Okay, so if the scene is relatively static, it could compress more aggressively, but if there's a lot of motion, it would back off a bit.
Exactly. And I think Regen's architecture could be adapted to do this. Like, you could add a module to the encoder that analyzes the motion and complexity of the video and then uses that information to control the temporal downsampling.
That's really interesting. What kind of benefits do you see that having?
Well, for one, it could lead to even more efficient video compression, especially for things like surveillance footage, where you have long periods of inactivity punctuated by short bursts of action.
Right. You wouldn't need to store all those redundant frames during the inactive periods.
Exactly. And it could also be really beneficial for generative models. You know, if you're trying to generate a video of a car chase, you want to make sure you capture all the details of the chase, but you don't need to spend as much computational effort on the parts where the car is just driving down a straight road.
Right. That makes a lot of sense.
Well,
Okay, what's the other novel notion you had?
Well, this one builds on the idea that Regen doesn't need to be pixel perfect. What if we explicitly incorporated predictive coding into the latent space?
Predictive coding.
Yeah, so instead of just trying to encode everything, what if the encoder specifically focused on encoding the unpredictable parts of the video?
Okay, I'm intrigued. How would that work?
Well, you could have the encoder output a prediction residual, which is basically a representation of the things that couldn't be predicted based on the previous frames.
This is like, here's the stuff that surprised me.
Exactly. And then the decoder, instead of trying to reconstruct everything, could focus its generative power on those unpredictable elements.
So it's like shifting the burden from the encoder to the decoder.
Yeah, and the idea is that this could potentially lead to even higher perceptual quality, even at very high compression ratios, because the latent space wouldn't be as cluttered with information that could have been predicted anyway.
That's really clever. It's like saying, okay, I know you're a smart generative model. I don't need to tell you everything, just fill in the blanks.
Exactly.
I love these novel notions. Really thought-provoking stuff.
Yeah, it's exciting to think about where this research could lead.
All right, so to sum it all up, Regen presents a really compelling new approach to video embedding. By focusing on plausibility over pixel-perfect reconstruction, they're able to achieve those impressive gains in temporal compression, which opens up a whole range of possibilities for generative models.
Absolutely. And the key takeaways here are that encoder-generator framework that diffusion transformer decoder, and that really clever content-aware latent conditioning module. These are all significant contributions to the field.
So for anyone out there working in video generation, I think this paper is definitely worth a close read. The link, as always, is down in the description.
And as you're reading it, think about how these ideas of prioritizing plausibility and efficient latent representations might apply to other areas of machine learning. It's a fascinating space to explore.
Absolutely. And as generative models become more powerful, the way we represent and compress the world around us is going to become more and more important. Regen might just be a key step in that evolution.
Maybe.
All right. Thanks for joining us on the deep dive. Until next time.
See you then.